just looking at what we have concerning rational functions. We looked at the other day, we were starting going into domain once again, along with vertical asymptotes in terms of how they tie in together. And again, just kind of going back to where we had left off and just looking at some items we have from your textbook in section 2.5, okay, and I did not assign these particular items, okay, the problems I did assign from section 2.3, and I've already posted the solutions to those, and again, section 2.3 was concerning polynomial division, like your line division, synthetic division, and also the remainder and the factor theorems. But now, in the case of what we have with rational functions and asymptotes, and again, we looked at vertical asymptotes, and again, in graphing, a rational function will never come into contact with any vertical asymptote. And looking at what we have in section 2.5, okay, so if we were to determine the domain and vertical asymptotes, if any, and for what we have in the case of the first item, we'll say we have for the case that we have in problem number 7, okay, and we have a given rational function, okay, where we have that y is equal to f of x. And we have equal to x squared minus 25. All over x minus 5, okay, and now for this ratio, okay, since this is a rational expression and since we cannot have zero valued denominators, okay, now any possible restriction will come from disallowing the denominator from being equal to 0. And if we have that x minus 5 cannot be equal to 0, well, in this case, if x minus 5 cannot be 0, we have furthermore that x cannot be equal to 5. And 5 is going to be the only restricted value. So right away, since x cannot be 5, and that also happens to be the only excluded value, okay, we have for the domain of this function. And if we display in interval notation, okay, so we have at the lower end, okay, we have what we can have for x will be those values less than 5. And in terms of what else x can be, it'll be for those amounts that will be greater than 5. Yeah, so that is going to be the domain. Okay, now where we have concerning the determination of any vertical asymptotes, and again, we are stressing, okay, putting the rational function in simplest form, okay, and if you notice, okay, we have for x squared minus 25, okay, that's going to factor to x plus 5 and x minus 5 since we have a difference of squares in the mix. Okay, so we have displaying x squared minus 25 in factored form. So you have x plus 5 times the quantity of x minus 5 and if you notice, okay, we have x minus 5 is present in both the numerator and denominator. So for the reduced form, okay, we're going to have the direct expression where we have x plus 5. Okay, and what this means is that in the cancellation step, okay, since the denominator completely cancels, okay, since this completely cancels out, okay, there will be a couple of things to spring forth. Okay, first of all, with the cancellation of the denominator, okay, there's going to be no vertical asymptote. And again, the exclusion from the domain was the restricted value of 5, okay, which could have been a vertical asymptote had x minus 5 not canceled. But for what we have instead is that with the cancellation, okay, we're going to have the x equals 5 is going to be a hole in the graph. So just looking at what we have on display, okay, for this particular rational function, okay, so you have the x and the y axis. And again, we had the restricted value of interest with 5. Okay. Okay, and just sort of highlighting this. Okay, so you have, in this case, right, so you have your graph for f of x. Okay, now, again, f of x reduces, okay, to x plus 5. Okay, but now the graph of y equals x plus 5, okay, would be a line that runs continuously. But since we did not start out at y is equal to x plus 5, but instead x squared minus 25 over x minus 5, this display, okay, signals that 5 cannot be in the graph. Whereas it would be if I had y is equal to x plus 5. But with this original display, you have the domain restriction. And so again, we have a hole at x is equal to 5. Okay. Now, for what we have in the case of the next item, okay, and we have another rational function, and we have in the form of g of x is equal to x squared minus 9 all over x minus 3. And so we have a difference of squares over a binomial. And looking for the domain, okay, now we have, once again, restricted that x minus 3 cannot be equal to 0. So just as 5 was the only value left out in problem 7, we have only 3 left out in problem 8. Okay, so we have for the domain, again, displaying in interval notation. Okay, so we have for the lower half of this set, okay, we have those values of x less than 3. And for the upper half, okay, we have those values of x which will be greater than 3. All right. Now, where we have looking at any possible existence of a vertical asymptote, and for what we have in g of x, Again, the numerator we have x squared minus 9, and looking at displaying the factored form. Okay, so I have the quantity of x plus 3 times that of x minus 3 all over x minus 3 x minus 3 is going to cancel out. And again, g of x reduces to x plus 3. So there's no longer the existence of a denominator. Okay, and so x minus 3 cancels out completely. Okay. And again, so we have that just as what we had earlier with x equal to 5. And we have that x equals 3 is a whole. And since 3 was the only restricted value from the domain, and since x minus 3 cancels out, okay, we have no vertical asymptote. And just putting on display, okay, the nature of the behavior of the graph, okay, which is going to be very much similar to what we had in problem 7. Okay, but this time we have the restricted value at 3. And once again, okay, we're going to have a whole at x is equal to 3. And for what we have in green, okay, that's going to be the graphing portions of what we have for g of x. And without the whole, we would have otherwise had a straight line running continuously from end to end. All right, now there is a situation, okay, where we can have no asymptotes, just like what we had in number 7 and 8, and also you can have multiple vertical asymptotes, and just sort of laying the groundwork. Okay, now in the next item, okay, where we have the function to already be displayed in simplest form, and let's say that if we have in number 17, okay, say we have our function f of x is equal to 8 over x minus 4. Okay. Right. And again, if we look for the domain, okay, again, we have the restriction that the denominator cannot be equal to 0. And if x minus 4 cannot be 0, okay, we have the x cannot be 4. And we have, in the case of the domain, we have those values of x less than 4, along with those values of x greater than 4. All right, now for the rational function, okay, f of x is already in simplest terms. And so what that means is that the denominator x minus 4 remains. And because it remains, okay, the exclusion from the domain, okay, is going to be the vertical asymptote. And just looking at what we have here. Okay, so we have a vertical asymptote at x is equal to 4. Okay. And we have with the nature of the graph, okay, what we have for f of x. Okay. Again, we'll look into further details, okay, regarding the dynamics of how, okay, these particular rational functions take shape. Okay, but right now, we've got a vertical asymptote at x is equal to 4. And for f of x equal to 8 over x minus 4, again, you have split up into two separate sections. All right. Now, for what we have in the case of problem 18, okay, so we have g of x is equal to 2 over x plus 7. And just looking at what we're going to have for the domain. Okay, so again, the denominator, x plus 7 cannot be 0. So we have that x cannot be equal to negative 7. Okay, so we have the domain will be split up into halves. Okay, so we have first half will be those values of x less than negative 7. And for the upper half, okay, we have those values of x which will be greater than minus 7. And just for the same reason, okay, now the denominator is going to remain, since g of x, like f of x earlier, is already in simplest form. And so the excluded value from the domain is going to be that which defines the vertical asymptote. So we have x equal to negative 7. Okay, so we have with the restricted value for x equal to negative 7, and again, the nature of the function is where we have x equals negative 7 is going to be the vertical asymptote. And for what we have in the case of the graph of g of x, and again, for the upper and the lower portions along x equals negative 7. Now, theoretically, okay, the graph will be getting closer and closer and closer to the vertical asymptote, but it will never come into contact with x equal to negative 7. So, again, vertical asymptotes will always be off limits where the graph of the rational function is concerned. All right. Now, okay, so we have with 17 and 18, okay, we have just one vertical asymptote, while numbers 7 and 8 did not have any, but we had in lieu of vertical asymptotes, we had holes in the graph instead with respect to the restricted values from the domain. Now, for what we have in the case of number 20, okay, now we have a function form of y is equal to k of x. Okay, we have is equal to x plus 2 And we have all over 3x squared plus 8x minus 3. All right. And looking for the restrictions in x. Okay. Again, the denominator cannot be 0 in value. Okay. And what I'll do here, okay, so this trinomial is factorable. What I'm going to do here, just kind of move to the side here. Okay, so if I'm looking at factoring this trinomial, okay, now you could do trial and error, especially since the coefficients are relatively low. But if we go with, say, the factoring by grouping approach, okay, so you got your first coefficient at 3, last at -3. Okay, so I have 3 times -3 is -9. And I want factors of -9 that will add up to 8. Okay. And again, we have worked with 3 and -3. However, 3 plus -3 will add up to 0. And again, I want the combination where the sum or difference will be on the plus side at 8. And okay, so I have more weight given to the positive factor than to the negative. Okay, so if we go with -1 and 9, -1 times 9 is -9, -1 plus 9 is 8. And that will be the combination we are seeking. Okay, so with -1 and 9, okay, if I split up the 8x into variable terms consisting of -1 and +9 as coefficients, so we have 3x squared minus x. We have plus 9x minus 3. And setting the stage, okay, for grouping. Okay, so if we group together the first 2 terms apart from the last 2. So the first 2 terms, I have 3x squared minus x. And the operation situated between the first 2 and the last 2 terms, okay, we have to be addition. We have times the quantity of 9x minus 3. And for what we have with the greatest common factors, for the first expression, okay, so we're going to have, in this case, we have x. X will go into 3x squared minus x, okay, which will be 3x minus 1. And for 9x minus 3, greatest common factor is going to be at 3. And into the quantity of 9x minus 3, okay, so we have 3x minus 1. And for the factors, okay, for that which is shared, okay, we have 3x minus 1. And with the outside terms in operation, okay, we have upon consolidating, okay, we end up with the other binomial factor at x plus 3. Okay, so just relaying back to what we have and determining the restrictions from the domain. Okay, so we have, again, so we have the factored form. So we have 3x minus 1 times the quantity of x plus 3. Once again, cannot be equal to 0. And if that is the case, right, so we have neither 3x minus 1 nor x plus 3 can be 0. Okay, and so if 3x minus 1 cannot be 0, okay, so you had that 3x cannot be equal to 1, And we have excluded from the domain, okay, will be the non-integer value in the form of the fraction 1/3. Now for x plus 3, if that cannot be 0, we have that x cannot be equal to -3. Okay. And so for what we have in the case of the domain of this rational function, okay, so between -3 and positive 1/3, -3 will be the lesser of the two restricted values. So we have for the domain, we have for the smallest set of values, and we have those values less than -3. And then next we had those values greater than -3 and less than 1/3 and 1/3 with 1/3 as the second and last restricted value. We have for the rest of the values in the domain will be those values of x greater than 1/3. And for what we have regarding the vertical asymptotes, okay, so again we have x plus 2 all over 3x squared plus 8x minus 3. And just looking at what we have in factored form. Okay, and again, factors of the trinomial. Okay, we have a 3x minus 1. And also we have x plus 3. And if you notice, k of x turns out to have already been in simplest form, for there is no common factor between the numerator and denominator. Okay, and so for what is going to happen in effect, okay, these items remain. So that means we're going to have a couple of vertical asymptotes. Okay, since 3x minus 1 did not cancel out, the 0 of this, again, is one vertical asymptote. And with x plus 3 still remaining in the denominator, its 0 forms the other vertical asymptote. And so for what we have, say just looking at it from a graphing standpoint, okay, so again we have two vertical asymptotes. Okay, so you have x equal to -3 as well as x equal to 1/3. And just for the nature of the graph of k of x, to the right of x is equal to 1/3. Okay, we just have hovering above the x-axis as we go to the extreme right. And for what we have in the middle, okay, to the left and the right of the middle section, left hand section have running tangent to -3 but never getting into contact, and that we have at the extreme bottom. Okay, we have the middle section runs tangent to but never coming into contact with x equal to 1/3. And for the rest of the graph, okay, to the extreme left, Okay, we're just going to have kind of stay below the x-axis. And the lower region, we have, again, running tangent, but never contacting x equal to -3. So these three sections will define, okay, what we have for this function, k of x. All right, and so, tell you what, we're going to make a bit of a transition over to other kinds of asymptotes. But I'll tell you what, just for right now, regarding domain and vertical asymptotes. And we'll be looking for the domain and the asymptotes. And we'll say we have with our function r of x is equal to, we'll say we have x squared minus 25 all over x squared plus 7x plus 10. Again, you do not have to grab. Okay, but let's see what we get for the domain and the vertical asymptotes, if there are any. Okay, if you're still working on this function, that's fine. Okay, so once again, looking for the restrictions from the domain and thus the domain as well as the vertical asymptotes, if any. Okay, so we have for this rational function, okay, looking for the restrictions. And again, for a rational function, okay, the denominator cannot be equal to 0. So we have the denominator at x squared plus 7x plus 10 again, so this cannot be 0. And we have with the trinomial, okay, we have factoring out to x plus 5 and x plus 2. And neither factor can be equal to 0. And we have, since x plus 5 cannot be 0, okay, we have the x cannot be -5. And since x plus 2 cannot be 0, we have the x cannot be -2. Okay, so we have not one but two exclusions from the domain with -5 and -2. So you have with what we have for the domain, okay, we have between -5 and -2. -5 is the lesser of the restricted values. So we have for the domain at the lowest end, okay, we have those values of x, okay, which will be less than -5. And progressing to the highest end, okay, we have in the process we have bypassing -5. And the next set, we have those values of x greater than -5 and less than -2. And with -2 as the second to last restricted value, we have at the extreme upper end what will be those values of x greater than -2. Now, in terms of what we have and finding out what the vertical asymptotes, if any, will be. Okay, so looking at what we have in the ratio. Once again, we have the reappearance, okay, from problem number 7 in section 2.5 with the numerator at x squared minus 25. Okay, and again, we have factoring out to x plus 5 and x minus 5. And we have with x squared plus 7x plus 10. Again, we have factoring. Okay, so you have x plus 5 and x plus 2. Okay, so here we're going to have the denominator factor x plus 5 to completely cancel. And the simplified form of what we have with r of x, okay, we're left with x plus 2 as the remaining denominator expression. Okay, so with x plus 5 going out, okay, so you have the x equals negative 5 is going to be a hole in the graph, and with x plus 2 remaining inside r of x when expressed in simplest form, okay, we have the vertical asymptote to be the zero of this. So we have a vertical asymptote at x equals negative 2. And again, with our restricted values of interest, we have negative 5 and negative 2. And again, the only vertical asymptote we have with x equal to negative 2. And for the graph of r of x, okay, so we got for the lower right hand section, okay, we have a kind of bow in this fashion, and then we have for the left hand section, okay, you have a bit up and to the left, and again, you're not going to have this portion to be running continuously since we have a hole at x equal to negative 5. And so these portions I have in green, okay, those will be referring to what I have for r of x equals x squared minus 25 all over x squared plus 7x plus 10. Okay, so far we have worked exclusively with domain and vertical asymptotes. Now, where we might have other asymptotes in the mix, okay, and we have included with vertical asymptotes, we're going to have what will be referred to as horizontal and slant asymptotes. And we have some rules of thumb to go by to determine if we have any of these items to exist for particular rational functions. And for horizontal and slant asymptotes, now I have some theoretical notation for a given rational function, which should be reminiscent of what we had in the case of just kind of setting things up for polynomial division, as we made the segue from line to synthetic division. And we have for a rational function, Okay, so here for a rational function, okay, where we have r of x is equal to, again, with the theoretical notation, again, this would be like the polynomial we had, setting things up for synthetic division. So you have like your a of n, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, and so on. Okay, so you have going to a constant where we have a naught, and we'll have all over b, and this time we have the sub and superscripted variable is going to be m. So you have b sub m times x to the m plus b sub x, not x minus 1, but m minus 1 times x to the m minus 1. Okay, so for this ratio of polynomials, where we're going to have that n is equal to the degree of the numerator and we have for m is going to be the degree of the denominator. Okay, now whether we're going to have horizontal or slant asymptotes will come down to what we have in comparing what we have for these powers. In other words, how the degree of n is going to compare to the degree m for the denominator. Okay, and we have now there are four possible scenarios. Okay, first of all, if it turns out that the degree n is less than the degree m, then there's going to be a horizontal asymptote, which will be y is equal to 0. Now, if it turns out that n and m have the same value, if n is equal to m, okay, then there's going to be a horizontal asymptote. And this will be taking the ratio of the highest degree terms. Okay, so this would come down to the ratio of the highest degree term coefficients, where we have a of n all over b of m. Okay, and for the next two cases, okay, this will be where n is greater than m. And if we have that n is greater than m by 1 degree, then there's going to be not a horizontal asymptote, but a slant asymptote. And this is going to be in slope-intercept form, but what I'm going to do here, since I'm already using up m and b, instead of the typical y is equal to mx plus b. I'm just going to say they have y is equal to alpha of x, alpha times x plus beta. And it serves the same purpose as y is equal to mx plus b. And if it turns out that n is greater than m by more than 1 degree, what's going to happen here is that you're not going to have any additional asymptotes. So if n is greater than m by more than 1, and just kind of put this in shorthand terms, okay, we have no horizontal asymptote as well as no slant asymptote. Okay, all right. So these are the rules of thumb to go by if we have the existence of horizontal or slant asymptotes. And let's say that in the case of just kind of melding together what we have had with domain and vertical asymptotes, and now looking at expanding the model to see if we had the existence of a horizontal or slant asymptote. And let's say that once again, so if we're looking at determining the domain, and instead of just the domain and vertical asymptotes, I'm just going to say determine the domain and the asymptotes. Okay, so we got for this one, okay. Let's say we have with our first rational function, and we'll have this already in simplest form. Okay, so you have the r of x is equal to 3x plus 1 all over x plus 2. Okay. Just going to mention in case you have this in simplest terms. And looking for what we have for the domain. Okay, so you have the denominator x plus 2 cannot be equal to 0. So if x plus 2 cannot be 0, so we have that x cannot be negative 2. So we have for the domain, okay, so we have those values of x less than negative 2, along with those values of x greater than negative 2. And again, since the rational function is in simplest terms already, okay, we have the restricted value negative 2 to already define what the vertical asymptote is. So the vertical asymptote, we have x is equal to negative 2. Now, in terms of any additional asymptote, okay, so I have r of x equals 3x plus 1 all over x plus 2. And okay, so for the degree of the numerator, okay, that would be first order as signaled by the x from the 3x. And for the denominator, okay, you also have to be a first order since we have first degree for the x in the x plus 2. Okay, so for what we have in the layout, so we have that n is equal to 1. And the denominator degree in x is also at 1. And for what we have in comparing, okay, so you have the n is equal to m. So there's going to be a horizontal asymptote, which is going to be the constant resulting from taking the ratio of the highest degree terms that exist. Okay, so you have case number 2 to apply. So you have the n is equal to m. So you have for the horizontal asymptote, we have that y is equal to the constant resulting from, again, the highest degree terms. From the numerator, I have 3x. From the denominator, I have x. And 3x over x goes to 3. So the horizontal asymptote is going to be y is equal to 3. And again, just looking at the rough appearance for what we have for this function. Okay, so we have a vertical asymptote at x equal to -2. We have a horizontal asymptote at y is equal to 3. Okay, so you have the vertical asymptote. Now for the horizontal asymptote, okay, so you got y equal to 3, x equal to -2. And for the graph itself of r of x, it's still going to be split up into 2 sections. And we have these portions be running tangent in fashion to both the vertical and the horizontal asymptotes. Okay. All right. So again, okay, so we have 2 asymptotes, one vertical, one horizontal. And now let's say that if I have another rational function, and let's say that we have that r of x, okay, is equal to 3 over x plus 4. And again, we have this rational function already in simplest form. Okay, so the denominator cannot be 0. So we have left out of the domain is going to be -4. Okay, so you have for the domain, you have those values of x less than -4, along with those values of x which will be greater than -4. And since the ratio is already in simplest form, okay, the exclusion from the domain will lead to the only vertical asymptote, again, which we have at x equals -4. and looking at the comparison of the degrees in the numerator and denominator. Okay, so again, we have the denominator, we have x, again, as the higher degree variable term, so we had the m is equal to 1. But now if you notice in the numerator, there is no appearance of any x. And so we're going to have the n is equal to 0. And again, the reason for this is that we have no x term in the numerator. Okay, so we got for the layout, okay, so we got no x term. And for what we have in the case of the degree comparison, okay, so 0 is less than 1. So you have the n is less than m. And here, if n is less than m, then there's going to be a horizontal asymptote, y is equal to 0. And y equals 0 is going to be the x-axis. And so for what we have in terms of, again, just doing a construction with the asymptotes and also the what we have in the domain, okay, is sort of our general guidelines. Okay, so we got x equal to -4, and y equals 0. Okay, that's just going to be the x-axis. And for the graph itself, okay, so now there are situations where the graph can come into contact with a horizontal asymptote, but in this particular case, it's just going to run tangent. But never is the graph of a rational function ever going to come into contact with a vertical asymptote. Okay, so this will be what we have in the case of r of x is equal to 3 over x plus 4. Okay, now let's say that if we have we have for a third case. Okay, let's say we have r of x is equal to x squared plus 5 all over x plus 1. Okay, now this ratio is already in simplest form. Okay, so if we go ahead and look for the domain, okay, so we have the x plus 1 cannot be 0. And so we have the x cannot be equal to -1. And we'll have for the domain, we have those values of x less than -1, along with those values of x which should be greater than -1. And since the ratio is already in simplest form, okay, the exclusion from the domain -1, this will turn around and be that which defines the only vertical asymptote. So we have x equal to -1. And in terms of any other asymptote, again, looking at the comparison of the degrees. Okay, so we've got in the numerator, we have the n is equal to 2, and in the denominator from x, which is to the first, we have m is equal to 1. And for what we have out of the scenarios, okay, so you have n at 2 and m at 1. And here we have, okay, so we're going to have that 2 is greater than 1 by 1. So in this case, there is going to exist a slant asymptote. And since we have a first order divisor in x plus 1, you can, now for the slant asymptote, okay, this would be the quotient as we take, in this case, x plus 1 into x squared plus 5. And you could arrive at this in either of two ways. Okay, so you have like x plus 1 into x squared plus 5. Okay, if you notice, we are missing the x term, so we're going to use a 0 placeholder. And again, we have with, say we go with the long division route. Okay, so you have x and x squared will go x times, and distribution of x over x plus 1, we're going to have x squared plus x. And we have upon subtracting, so we have x squared minus x squared goes out. And we have 0 minus x, so we have negative x plus 5. Now I can take x into negative x, which will go negative 1 times. And so we have negative 1 times x is negative x. Negative 1 times 1 is negative 1. And subtract, so we have negative x, so it's going to be plus x goes out. 5 minus negative 1 becomes 5 plus 1, which will be 6. So 6 is just going to be a remainder, and we cannot take x directly into this. So we have the quotient at x minus 1. I'm just going to mention, had you decided to go with, or if you were to decide to go with synthetic division, so we have x equal to negative 1, going the synthetic division route. Okay, so we got negative 1, and then we have 1, 0, and 5. Again, with synthetic division, you're looking at column by column addition. Okay, so leading coefficient of the dividend is brought down. Okay, then we have negative 1 times 1 is negative 1. And we have 0 plus negative 1 is negative 1. Negative 1 times negative 1 is a positive 1. And 5 plus 1 is 6. Again, we have the remainder equal to 6. And for the 1 and the negative 1, this will be in reference to the quotient, which you have at x minus 1. Again, we have the quotient at x minus 1. And that is going to define, okay, what we're going to have for the slant asymptote. And so we have with the slant asymptote, okay, we're going to have that y is equal to x minus 1. So just kind of bringing it all back together. Okay, so the domain is exclusive of -1. And again, since x plus 1 is in the denominator and the ratio is already in simplest form, x plus 1 remains. So the exclusion is going to be that which defines the vertical asymptote, x equal to -1. And again, on the basis of how the degrees between the numerator and denominator compare, we end up with a slant asymptote at y is equal to x minus 1. And looking at what we have from a visual standpoint, and I think I have this one stored. Let's see. I may or may not. Let's see. Yeah, it turns out that I do. Okay, so we got for the sections case, I have a couple of broken red lines. And again, just for that which runs vertically. Again, this is going to be in reference to x is equal to -1. And for the dashed line, okay, that is running diagonally, this is going to be in reference to what we have with y is equal to x minus 1. And then we have for the sections, okay, we have kind of going in and out. Okay, these two sections. This will be for what we have in reference to r of x is equal to x squared plus 5 all over x plus 1. All right. And I'll tell you what, just for the next few moments, and say if we were to determine the domain and asymptotes of the following functions, and we'll have these almost identical, and we'll say that we have for r of x, okay, we'll say that we have r of x is equal to let's say I have is equal to 4 over x plus 1. And we'll say that we have r of x is equal to, let's say we have 4x plus 8 all over x plus 1. So for the next few moments, let's see what we get for the domain and asymptotes, vertical, horizontal, slant, wherever they may exist. Okay, and we'll discuss in the next few minutes. Okay, tell you what, for these two functions, okay, we have the same denominator. Both ratios are already in simplest form. Okay, so we can go ahead and tackle the domain for both of these. Okay, so again, x plus 1 cannot be 0. So we have x cannot be -1. And both of these rational expressions will have the same domain. You can have all the values of x except for -1. Okay, and since both of these ratios are already in simplest form, okay, the restricted value of -1 is going to be the vertical asymptote. Okay, so we got for, okay, so we got the same domain and the same vertical asymptote. And for the items of concern, okay, this is where the similarities are going to end. Okay, so we got so we got the same domain, same vertical asymptote. Now for the first rational function, okay, we have r of x equal to 4 over x plus 1. Again, we don't have an x term. So again, we have n equal to 0. Again, just restating the reason. And we have from x plus 1, okay, like x to the first. So we have that m is equal to 1. So n is at 0, m is at 1. And in terms of the comparison of degrees, so we have that n is less than m. Again, we have among our four cases where n is less than m. Again, we have a horizontal asymptote right away, which is going to be the x-axis, namely y is equal to 0. All right. And in terms of what we have from a graphing standpoint, you see have x at -1. So again, we applied the vertical asymptote as such, and again we have a horizontal asymptote, y is equal to 0. And for what we have in the case of what we have in the interaction, okay, and so we're going to have just for the general graph in this case, And again, the asymptotes will split the graph of r of x into two separate sections. All right. Now, for what we have in the case of our other function, okay, so for 4x plus 8 over x plus 1, again, both of the variable terms are of first degree. So we have n is equal to 1. Then we have the m is equal to 1. Again, we have the second case once again to apply where we have n is equal to m. And instead of a horizontal asymptote, y is equal to 0, we will have a non-negligible horizontal asymptote. Again, that will be the coefficient formed by taking the ratio of the highest degree terms. Okay, so in this case, we have y is equal to 4x from the numerator over x in the denominator. And so we have, for the horizontal asymptote, we have that y is equal to 4. Again, for the numbers of interest, okay, so you have on the x-axis we have -1, and the y-axis, okay, we have at 4. So again, we have with the asymptotes, again, we have y is equal to 4, and x equal to -1. And just for the construction of what we have here, okay, let me, looks like I'm going the wrong way. Here we go, okay. And again, I'm not drawing this according to scale by any stretch of the means. Okay, so for what we're going to have in this particular case, right? So again, this is kind of a crude construction, but you will have a section that's going to be where the asymptotes intersect. You'll have a section that's going to be up and to the right, and also a section that's going to be down and to the left. So this will be for what we have in the case of r of x. Okay. Now, just one more case here, and this is we'll let this be our last example. And we have say we have with r of x, and this is going to tie in, okay, just some of the fundamentals from section 2.3 when we had polynomial division. And say we have for r of x, okay, so you have x cubed plus 5x squared plus 3x plus 1 And we have all over x squared plus 1. Okay. Now looking for the domain as well as the asymptotes. Now this is a special case, and it's been a while since we've seen one of these, especially where you have a sum of squares in the denominator. Okay, so just kind of a refresher. Okay, now the restriction is that we cannot have a zero denominator. So x squared plus 1 cannot be 0. And now, while I can factor in terms of integer coefficients within the real numbers, okay, I can factor a difference of squares, but I cannot factor a sum of squares. But what I can do is I can move the 1 over. So I have like x squared cannot be negative 1. And from the square root property, so if x squared cannot be negative 1, well, we have that x cannot be plus or minus the square root of negative 1 and we have that x cannot be plus or minus I. But guess what? The only excluded values are from the complex number system. And so we have abandoned the complex number system for this part of the course. Okay, so there are no real values excluded. Okay, so that means that the domain is going to be the set of all real numbers. Because anything that x cannot be, well, guess what? Just complex numbers, plus I, negative I, and we're not even worrying about that with the real number system. All right. Now, for what we have in terms of the ratio itself, again, coming down to the comparison of degrees. Okay, so we have at the top, okay, the highest order term is going to be x cubed. So we have n is equal to 3 in the denominator. Okay, we have the degree to be at 2. So we have n is equal to 3. M is at 2. And so you have that n is greater than m by 1. Okay. And let me pause just for right now. Okay, so we cross over to the comparison of the degrees. Okay, now let me mention something too. Okay, so the domain we're going to have as a set of all real numbers. And anytime you had the domain to be the set of all real numbers, okay, because you had no real values are excluded, there's going to be another item too. If there are no real values excluded, remember, we had the formation of vertical asymptotes from exclusions from the domain, okay, whose factors remain in the denominator. But if there are no real values excluded, there's going to be no vertical asymptote. Now previously we had no vertical asymptote on the basis that the exclusions converted into wholes, but under these conditions you're not going to have even a hole in the function. So there's no vertical asymptote, no hole, or any of that. Now in terms of any asymptote period, okay, so this will come down to the comparison of degrees in the numerator and denominator. So n is at 3, m is at 2, n is greater than m by 1, and so this is going to be an application of what we have in the third scenario. n is greater than m by 1. So there's going to be a slant asymptote. And that is going to be the quotient upon taking the denominator, which is going to be the divisor, into the numerator. So for what we have here, okay, now if you notice, we have from the second degree in x, we cannot use synthetic division directly. Or automatically. Okay, and just setting things up along the lines of long division. Okay, now it's not so mandatory that you have 0 placeholders in the divisor, as would be the case had we faced the lack of any x term between the third order and the constant. But we'll just kind of use placeholder for the divisor. That part is optional. Okay, so if we look at x squared into x cubed, now the first term of the quotient is going to be x. And if we distribute, so you have x times x squared is x cubed. X times 0x, well, that's just going to be 0x squared. Again, just for placeholder purposes. And we have x times 1 becomes x. And looking at subtract, so x cubed minus x cubed goes out. 5x squared, okay, minus 0, so we still have 5x squared. 3x minus x is going to be 2x. And we can bring down the plus 1. So I took x squared and x cubed, and I can take x squared directly into 5x squared 5 times. And distributing 5 over x squared becomes 5x squared. And 5 over 0x, again, so I have 0. And 5 times 1 is 5. And looking at subtracting, okay, so you have 5x squared minus 5x squared will go out. 2x minus 0 becomes 2x. 1 minus 5 becomes negative 4. And now, while I was able to take x squared into x cubed and x squared into 5x squared, since the leading terms were greater than or equal to the degree that we have for x squared, I cannot take x squared into 2x minus 4. So 2x minus 4 will be the remainder, and we're not concerned with that. We're concerned only with the quotient in terms of finding out what the slant asymptote is going to be. And for that slant asymptote, we had that y is equal to x plus 5. Okay, so again, the domain consists of all real numbers, and there's only one asymptote that exists, and that's just going to be the slant asymptote. And again, there was no vertical asymptote since, again, we had no real values excluded from the domain. So there's nothing that could be, in a sense, recycled and be converted to a vertical asymptote. And just looking at what we have, And so for the graph, okay, that we have here. Okay, now for that which is in red, okay, that is the function we had with r of x. And for what we have with the slant asymptote, now just mention here, if you notice, okay, you have in this zone, okay, so you have the slant asymptote running tangent to the extreme and to the extreme right along, okay, the rational function. But if you notice, you had the slant asymptote was above, and once we get, okay, just a little bit to the right of the y-axis, okay, say around x is equal to 2, okay, notice you have an interchange from being above to finally being below. And again, r of x can come to contact with horizontal asymptotes and slant asymptotes. But never vertical asymptotes. Okay, so only vertical asymptotes are going to be off limits, but under special circumstances, you can have r of x to intersect or touch horizontal as well as slant asymptotes, but never vertical asymptotes.